Good morning, students. So, in software engineering and testing paper, we were learning about the SASD methodology, software analysis and structured analysis and the structured design methodology. In the previous class, we have learned about how to develop a DFD model of a system, and we see what is a context diagram, how to develop the context diagram, and following lower level diagrams, DFD diagrams in a hierarchy. Okay, now next one is the structured design. As we have learned earlier, in structured analysis, we form the DFD model of a system out of the SRS document. We analyze the SRS document to know the main functionalities, and we split the main functionalities into sub functionalities and form the DFD model of a system. The DFDs are always formed in a hierarchical order with a root or with a high level DFD, that is our context diagram at the top level of the DFD, and all the other high level functions are split up into sub functions to form 3 to 7 bubbles in lower levels of data flow diagrams. We may have up to level 4 hierarchy of DFDs for any system, not more than level 4 and not more than 3 to 7 bubbles per DFD hierarchy. We have learned all that things, and after forming the DFD model of a system, the next step is our structured design. During structured design, the DFD will be transferred into a structure chart. The formation of structure chart of a system is done during the structured design process. So, the aim of the structured design is to transform the result of the structured analysis. Always the result of a structured analysis is the DFD. During the structured analysis, we develop a DFD for the model. So, this DFD will be converted into a structure chart. A structure chart is usually a flowchart like representations. We use similar symbols for representing the flowchart also. It represents the software architecture. So, based on this structure chart, the implementation, further implementations of the system is to be done using this structure chart. Further design techniques, that is to design the algorithms or the structure chart forms the basis for the implementation of a software in any development language. So, it represents the software architecture, and it represents the various modules in a system, and also it represents the module dependency. So, structure chart represents the various modules making up the system and the module dependency, that is how a module calls between other modules, and the parameters that are passed among the different modules. So, the structure chart forms a basis for any process, any problem to be implemented using some programming language, as it represents all the various modules and module dependency and all the parameters used in a software. It is easy to refer to a structure chart to implement the software using any programming language. But the structure chart does not be used to represent the procedural aspects. That means how to implement a particular function, etc. The procedural aspects should not be mentioned using a structure chart, because the main focus of a structure chart representation is on module structure of a software, and different interactions among the modules should be specified. Structure chart is used to specify various modules used in a software and the module interaction in a software and also the parameters used in the software, and it should not be used to convey the procedural aspects of the software. So, procedural aspects are not represented using a structure chart. Let us see how will you build a structure chart for a system. The basic building blocks using the structure chart are designed using the following shapes. First one is a rectangular box. We use the rectangular box to represent a module, and each rectangular box will be named of the module itself. The name of the module will convey the function of that module. So, this will be the name of the rectangular box also. So, every rectangular box represents a module, and every rectangular box is named with the name of the module. That means the function of that module will be the name of the rectangular box. Second one is the module invocation arrow. The arrows connect two modules. That means an arrow connecting the two modules implies that during program execution, control is passed from one module to the other in the direction of the connecting arrow. So, this module invocation arrow represents the module call from one module to another. The control of or transfer of control from one module to other module is represented using the module invocation arrow. But we cannot convey whether the module will be called a single time or many time. The details of module calls will not be exhibited using the module invocation arrows. Just it represents a module call for another module, but how many times the module will be called will not be exhibited using the module invocation arrows. Next one is the data flow arrows. Data flow arrows represents the flow of data from one module to another. It is also small arrows. The data flow arrows are small arrows appearing along the module invocation arrows, and these are also named with the data name itself. The data flow arrow represents the flow of data from one module to another, and this is also represented with small arrows alongside the module convocation arrows. But these arrows may not be necessarily there in all the structure charts or with all the modules in a structure chart, and this naming is also done with the name of the data itself. The data flow arrows are annotated with the corresponding data name, as it is done for the modules. The name of the modules will be the function of the module. The same way, the data flow arrows are named with the name of the data itself. It represents the fact that the named data passes from one module to another in the direction of the arrow. The direction specifies the flow of data from that particular module to another module. Next one is the library modules. Library module is represented by a double-edged rectangle. The libraries contains all the modules that are frequently being used in a software. So, it is a collection of modules represented with double-edged rectangle. Usually when a module is invoked by many other modules, it is made into a library module. That means frequently used modules will be collected with on a library. Selection, the diamond symbol. There is a selection symbol. A diamond symbol is used for selection. It represents that one module of several modules connected with the diamond symbol is invoked depending upon some condition. Depending upon some condition, one of the modules from various modules will be selected. It is the same as we use the diamond symbol for representing condition in a flowchart. And likewise, here also the selection is represented using diamond symbol, and based on the condition given on the diamond symbol, some or one of the module among the various modules will be selected or invoked. Then repetition. Repetition is represented with a loop. A loop around the control flow arrows denotes that the respective modules are invoked repeatedly. The same loop that we use in the flowchart, that is used in structured chart to represent that some modules are invoked repeatedly. And in any structure chart, for example, a structure chart with some modules are given as example here. An example of a layered design and a poorly layered design. As we see, the structure chart always contains one module at the top, exactly one module at the top of the structure chart that forms the root module. And there should be at most one control relationship between any two modules in the structure chart. When we analyze this structure chart, a layered structure chart, that is a properly arranged, properly ordered structure chart. In this, we use M1. M1 specifies the module, that is the root module in the structure chart, that is at layer 0. And when we arrive with the layer 1, we see the module invocation arrow specifies the function or the module call to another module. This arrow is the module invocation arrow. It specifies that M1, the module M1 root module, calls other modules M2, M3 and M4. There is exactly at most one control relationship between any two modules in the structure chart. That means M1 calls for M2, but M2 does not exhibit any call to M1. That means if module M1 invokes module M2, module M2 cannot invoke module M1. The reason behind this is that we can consider the different modules of a structure chart to be arranged in layers or levels. Always these are arranged as particular layers. At layer 0 we form the root module, at layer 1 we form the modules that are invoked or called by the root module. So in this case the root module is M1 and all other modules M2, M3 and M4, all the modules that are being called by M1. At the same time, the module invocation arrows also specify that M1 calls for M2, M1 calls for M3 and M1 calls for M4. But there should not be any reverse call from M2 to M1, because all these are arranged as particular layers or levels. There should be at most one control relationship between any two modules in a structure chart. And the principle of abstraction also does not allow lower level modules to be aware of the existence of higher level modules. At any time, lower level modules, that is the M2, M3 and M4 should not call for the module M1, because M1 is the higher level module and M2, M3, M4 are the lower level modules. The principle of abstraction does not allow lower level modules to have to be aware of the existence of a higher level module. But it is possible for more than one higher level module to invoke another some lower level modules. Two or more higher level modules can invoke a smaller level modules. Here M3 and M4 are higher level modules comparing with M5. So more than one module, that is M3 and M4, can invoke a call to M5 because M3 and M4 are modules that are higher than M5. So more than two higher level modules can invoke same lower level modules, but the lower level modules cannot invoke the higher level modules. So this forms an exact example of a layered design, and see the difference between a properly designed structure chart and a poorly layered design. Here each layer 0, layer 1 and layer 2 exactly specifies how the modules are represented and how the modules call for another module. The module interaction is exactly specified, properly specified in this case with the exact layers. But for a poorly layered design, see how the repetition works and how difficult it is to understand, because it specifies a lower level module invoking a upper level module, higher level module, and how poorly the loops, the repetition is specified in this. So this is a poorly layered design. As we have said, the structure chart uses many of the symbols that are being used in a flowchart. As we know, flowchart is a convenient technique to represent the flow of control in a program. Flowchart is always used to represent the flow of control in a program. Likewise, in a structure chart, we make use of various symbols like that in flowchart to represent the flow of control in a program. But still there is some difference between the flowchart and a structure chart. The three principal ways in which a structure chart differs from a flowchart are given as: it is usually difficult to identify the different modules of a program from its flowchart representation. As it is said, a flowchart represents the flow of control from different parts of the program, but using a flowchart we cannot predict or we cannot identify the modules of a program. In structure chart we use modular specification and a layered approach. Both of these, modular specification and the layered approach, will not be used in a flowchart. It simply depicts the flow of control in a program, but not in a modular way or not in a layered manner. So that is the foremost difference between the flowchart and a structure chart. Second difference is that data interchange among different modules is not represented in a flowchart. A flowchart merely represents the flow of control in a program and not the data interchange among the modules. There is no module specification in flowchart and there is no specification of data interchange among the different modules. But the data flow among the modules can be well represented using a structured design. That is using a structure chart that is being represented using data flow arrows, and the arrow points the data flow from one module to another, which is not at all possible using a flow chart representation. And the third one is the sequential ordering of tasks that is inherent to a flow chart is suppressed in a structure chart. Always a flow chart represents the flow of control in a sequential ordering. It is represented in a sequential ordering of flow of control. But the structure chart always represents the modules. It highlights for the modules and the module the data interchange among the modules. So it is arranged in module wise. So the higher level module calling the lower level modules, that the module interface will be highlighted in the structure chart, and it does not represent the sequential ordering of task because it just ignores about the procedural aspects. How a function is to be implemented is not at all represented using a structure chart, as it ignores the procedural aspects of a program, a structure chart will not represent the sequential ordering of task functions in a program. It simply it is used to specify the modules of the program and the data interchange between the modules. So, these are all the difference between the flowchart and the structure chart. There is difference, but still structure chart make use of the same symbols that is being used to represent a flow chart. The next one is the detailed design. In the structure design, we form a structure chart from the data flow diagram. In detailed design, during the detailed design, the pseudocode description of the processing and the different data structures are designed for the different modules of the structure chart. As we have learned earlier, the SASD methodology specifies a structured analysis and structured design of the problem. So, during the structured analysis, we form a data flow diagram from analyzing the SRS document. By analyzing the SRS document for its main functionalities, we form a data flow diagram from the SRS document that is being done on the software analysis process. And next, during the software structured design process, we form a structure chart from the data flow diagram. So, the data flow diagram is converted to a structure chart during the structured design, and immediately after getting a structure chart, after forming a structure chart, we go to the detailed design. So, the detailed design is the phase during which we form an algorithm or pseudocode from the module specification document. That is always the structure chart is used for implementing the software, because the structure chart contains all the module specifications, modules and the data interchange between the modules. We can directly transform the modules into particular functions. So, it is easy to implement algorithms and data structures from a structure chart. This is done using in the detailed design. So, in detailed design, the pseudocode description of the processing and various data structures are implemented from the structure chart. And these pseudocode or the data structures for the implementation of functions specified on the modules will be specified in a module specification document. So, all these pseudocode, algorithms and the data structures are described in the form of module specification document. Module specification document is always written using structured English. In a module specification document, the non-leaf modules describe the different conditions under which the lower level modules should perform. So, the non-leaf modules specifies the responsibilities of the lower level modules. In any case, the modules should specify the responsibilities of the just lower level modules. And the module specification for leaf level modules should describe in algorithmic form how the primitive processing steps are carried out. So, all the steps, all the functionalities, implementation of functionalities of each and every modules, whether a high level or the lower level modules, should be specified in an algorithmic form in the module specification document. So, all the functionalities could be implemented in any algorithm, pseudocode form or data structures, and these are all specified in a module specification document, which specifies all the functionalities of each and every modules with functionalities of the lower level modules also. Hope you understand. Thank you.